Welcome to the Ingesting and Preparing Data module. This introduction section describes the contents of the module. This module builds on the concepts presented in the prior modules. In this module, the focus is on the extract, transform, and load tasks that are part of ingesting data into your pipeline. The module compares the extract, transform, and load ETL and extract, load, and transform ELT approaches. It also introduces the steps involved in wrangling data to use in your pipeline. The objectives of this module are presented across multiple sections, each with their own video. The module wraps up with a sample exam question. This section looks at the high-level processes that are used to ingest data into an analytics pipeline. This section also compares ETL and ELT. In the Data-Driven Organizations module, you learned about the layers of a data pipeline. This simplified drawing represents that pipeline and shows each layer as distinct. In practice, ingesting data is about getting data from an external source into your pipeline where the data can be used. The process is tied to the tasks of storing and processing data. Specifically, the ingestion process incorporates extracting data from a source that isn't already in your pipeline, loading the data into some type of temporary storage in the pipeline, and processing the data by transforming it before or after the data is loaded into more permanent storage. The type and scope of transformations, where they occur across the data pipeline, highly depend on the business need and the nature of the data that's being ingested. This slide mirrors the layers that were depicted on the previous slide and compares two methods of ingesting data. You need to extract data from a source and then use a combination of loading the data into storage and transforming or processing the data for its intended purpose. The traditional method of ingesting and preparing data for analytics was ETL. With ETL, data is extracted from its source, transformed into a structured format that is ready to be used in analytics applications, and loaded into structured storage, such as a data warehouse. Data scientists or analysts query the data warehouse and might perform additional transformations and processing as part of their analyses. As described in the Design Principles and Patterns for Data Pipelines module, data stores evolved from handling only structured data to include options for handling high volumes of unstructured data. Specifically, there has been a move from structured data in warehouses towards unstructured and semi-structured data in data lakes. Tools and methods for ingesting data into a pipeline evolved along the same lines. ETL techniques have continued to evolve and are still a valuable part of data architectures for structured data. However, the trend towards collecting high volumes of unstructured and semi-structured data and the desire to make that data available for a variety of uses led to a different approach for data ingestion, ELT. With an ELT approach, data is extracted from its source and transformed only enough to store it in a consumable but relatively raw state in a data lake. Transformations that might be needed for specific use cases are done later, as consumers access data and build analytic solutions with it. In addition to the general guidance that works well for structured data that is destined for a warehouse, and ELT works best for unstructured data that is destined for a lake, there are other reasons to choose one or the other. This slide highlights a few considerations. ETL stores data that is ready to be analyzed, so it can save time for an analyst. If analysts routinely perform the same transformations on data that they analyze, it might be more efficient to incorporate those transformations into the ingestion process. So with ETL, you trade longer transformation processing time before the data is available for faster access when you're ready to query it. Another advantage of performing transformations up front is that you can filter out personally identifiable information, or PII, or other sensitive data that could create a compliance risk. If you never store the sensitive data, you reduce the risk without the need to evaluate additional security measures. On the other hand, ELT provides more flexibility to create new queries because analysts have access to greater amounts of raw data. With ELT, the process to get the raw data into your pipeline can be quicker because you aren't required to transform the data as much before making it available in the data lake. So with ELT, your trade-off is that you get the raw data available more quickly, but you spend more time to transform the data when you're ready to work with it. Another advantage of storing the raw data and only transforming it downstream is that changes to the transformation, for example, including additional fields or formatting data differently, would be run against all the historical data that was loaded when the transformation is updated. If the transformations occur before you load the data, your changes can apply to new data as it's being ingested, but it might be impossible to apply them to historical data. As other modules also note, how you design your ingestion process really depends on the business problem that you're addressing and the trade-offs that make the most sense for your use case. The design is likely to evolve based on both the builder's experience and the pipeline user's experience. In modern architectures, ETL and ELT approaches are blurred. Each role that works with the pipeline might perform a different part of the ingestion and transformation process by using different tools and access. For example, the data engineer might use an ingestion tool that handles common cleaning or formatting transformations before loading a dataset into your lake. Additional transformations might occur only when the data is pulled for a particular analytics use case. The data analyst might apply a set of transformations on the ingested data to prepare it for a specific report. A data scientist might perform additional discovery and transformation on the ingested data to investigate hypotheses about relationships within the data. As patterns of use and understanding of the dataset evolve, you might revisit where and how transformations occur. For example, if many analysts perform the same recurring transformation to work with the dataset, adding those transformations into the processing that occurs before the data is loaded might improve performance or reduce cost. Alternatively, you might recognize additional needs that you could serve by reducing the amount of transformation that is performed before loading the data. For example, you might truncate a large field to save cost, but a data scientist determines that there's value in the truncated field and asks you to remove that transformation. As the data engineer, you want to monitor how the pipeline performs, how it's accessed and used, and how you might modify your processes to optimize the value. Here are a few key points to summarize this section. Ingestion pulls data into the storage layer and applies transformations to it. Both ETL and ELT are common approaches to ingest data, with ETL being more geared towards structured data and ELT being more for unstructured data. This section looks at the high-level processes to prepare data as it is ingested into an analytics pipeline. Regardless of when data is transformed, the data engineer needs to develop methods to extract and combine disparate data sources into a useful data set. Data analysts and data scientists need to explore data, test hypotheses, and determine how to enrich or modify their data set to meet their business needs. The term data wrangling reflects the complexity and messiness of transforming large amounts of unstructured data or sets of structured data with multiple schemas across multiple sources into a meaningful set of data that has value for downstream processes or users. The content in this module takes the perspective of the data engineer. However, data engineers, data scientists, and data analysts might each perform different types of wrangling based on what they need from the data and the state of data that they start from. For ML applications in particular, a data scientist might perform lots of iterative wrangling to get a data set that is suitable for building and training an ML model. The Elements of Data module introduced this slide to illustrate how an organization might combine different data types to create a personalized customer experience. The organization can combine customer data from the on-premise database with public health data to personalize information for a patient. Patients might have a mobile app that sends real-time data that could be used to alert the patient or their doctor of a potential issue. With the data available, data scientists can build machine learning models to provide personalized predictions. As the data engineer, you need to figure out how to pull all this data together and make it available in your pipeline. This slide presents the steps of data wrangling as distinct. In practice, there might not be clear delineations between the steps, there might be iterations within and across steps, and individual steps might not occur as part of ingesting a data source into the pipeline. Each step might be more or less complex depending on the goal of the specific ingestion that you're working on. The ingestion and data wrangling process could be as simple as opening a source file in Microsoft Excel, manipulating columns and values in a spreadsheet, and then manually checking the validity of the data, and then saving it as a CSV file and uploading it to pipeline storage. At the other end of the spectrum, complex transformations might be needed to support high volumes of incoming data for an ML application. The data engineer and data scientist might use a variety of scripts and tools to wrangle the data for that kind of use case. As illustrated on this slide, the steps of data wrangling generally coincide with the steps of ETL processing. However, it's worth making a distinction here between ETL processing and data wrangling. Traditionally, ETL processing has been more of the data engineer's domain. ETL encompasses scripting transformations within batch jobs that run on infrastructure that's controlled by IT. Analysts and data scientists worked only with data that was in a defined consumable state. Data wrangling is more associated with an ELT flow, where business users or data scientists transform data sets that are available to them within the pipeline storage layer, but that haven't been refined for a specific use case. The continuing trend in cloud tools and services is to provide more types of users with direct access to extract and transform data. A data engineer must be able to build complete analytics pipelines and transform data as needed for a use case. But it's also important to stay aware of tool updates that can provide their team's analysts and data scientists with more autonomy to work with available data. It's important to remember that the defined layers help to describe the activities that are performed and tools that are used as data moves through and is transformed in the pipeline. But pipeline activities are iterative within and across layers. Each pipeline's architecture might look quite different depending on the business problem being addressed, the type of data being ingested, and even the skills and expertise of the team that supports the pipeline and accesses the data. This diagram is derived from the modern data architecture in the Design Principles and Patterns for Data Pipelines module. The diagram illustrates an ELT flow and highlights how the data wrangling steps might occur. In this reference architecture, data is ingested into a storage layer that includes Amazon S3 as the data lake and an Amazon Redshift data warehouse. Within the data lake, S3 buckets are used as named zones to store data in different states. The landing zone bucket serves as temporary storage from which you perform just enough cleaning and validating to permanently save the ingested data into the raw zone bucket. You can then use data in the raw zone for additional use cases. This data might be structured, semi-structured, or unstructured. At this stage, the initial extract and load steps are complete. In this example, the transform part of ELT occurs when data in the raw zone of the data lake is transformed into a highly structured state that the Redshift data warehouse can use. The data engineer or scientist would need to structure, enrich, and validate the data before the warehouse can use it. Data is stored in different zones as these steps are performed. Data structuring prepares the data for the trusted zone. Then data enriching is performed on data in the trusted zone, modeling the data so that it can be joined with other data sets and stored in the curated layer. Data validation would also occur as part of these transformations before storing data into the next zone. Data sets in the curated layer are ready for the Redshift data warehouse to ingest. If the process to load data into the data warehouse had been accomplished using a traditional ETL flow, the same wrangling steps would still be needed. However, all the transformations would have been performed on the data in a temporary staging location before the data was loaded directly into the data warehouse. Users would not have access to the data until processing was complete, and the raw data would not be available. The next section looks at each of the steps in the wrangling process in a bit more detail. Here are a few key points to summarize this section. Data wrangling is a multi-step process with steps that overlap and iterate differently depending on the data source and the use case. Data wrangling steps include discovery, structuring, cleaning, enriching, validating, and publishing. This section looks at the data discovery step of the data wrangling process. The data discovery step is iterative, and different roles, analyst, data scientist, data engineer, might look for different things at this step. As a data engineer, you need to find sources that you think might be useful, query them, and analyze the raw data to decide whether the sources have value for your business purpose. An analyst or data scientist might tell you about a source that they want to use. What you learn from your initial results might lead you to refine your queries and analyze the updated results before you decide how to use each source. Key tasks of this step include the following. Decide if a source seems to serve your business purpose. If it does, then you want to dig deeper into the data to do the following. Identify what relationships exist within and between the raw data sources that you expect to use. Identify the data formats, for example, CSV, Parquet, Optimized Row Columnar, or ORC. Determine the range of data that you want from each source, for example, a time period or a range of attribute values. Determine how to get the desired range out of the source and into your pipeline. Determine how you should organize the data to make it easy but secure to access and cost-effective to ingest and store. For example, what folder structure is appropriate? What's the best way to manage file size? How should you partition your target database table? You might need to choose a partition key that optimizes performance for your use case. Or you might need to establish folder structures in Amazon S3 to provide granular access to different parts of the dataset to different users. For example, you might create Amazon S3 folders for a particular segment of data so that you can grant access to each folder only to the team members that are authorized to access that segment. Your decisions about organization should also consider the structure that you want to use as part of the data wrangling process. For example, you might use the zone approach, which was illustrated earlier, to segment data that comes into the data lake into raw, landing, and trusted zones. Based on your analysis of the data relationships, formats, and organizational requirements, determine what tools you need. Also, determine what you have available to store, secure, transform, and query the type of data in each source. Consider whether you have the skills and resources that are needed to extract data from the source and prepare it for use. Based on these discovery activities, you might decide to work with the source, or you might determine that the effort and cost to extract and prepare the data for the intended purpose doesn't provide enough value. If you determine that it's not worth the effort, you might start the whole process again and seek additional sources, or look for ways to reduce the volume of data to be ingested, amount and type of storage that are required, or the complexity of preparing the data for use. The example scenario used over the next slides is based on a company with a software as a service or SaaS product. They recently acquired a startup company. A data engineer needs to provide customer support ticket data from the two products to support exploration of relationships between customer support experiences, ticket volumes, and contract renewals. The startup product is still currently supported by a different customer support team and system. The analyst wants the number and types of technical issue tickets worked on or closed during 2020 by customer, and they want each regional sales team to have access to their customers only. The sales analytics pipeline currently houses customer data in the data warehouse, but no customer support data. The next few sections will use this simplified ingestion example described on this slide to walk through each step in the wrangling process. For the initial discovery step, the data engineer might look at the fields and data that are available in the source data for customer support tickets. The engineer might also determine which information that is stored in the data warehouse is related to the business need. Based on this, they would determine how to get the desired data out of the source and into their pipeline. Looking at these table structures, what do you think is relevant to the request? This slide looks at the data discovery tasks for this scenario. The first relevant relationship is that the requester ID in Support System 1 is equivalent to the cust.num field in Support System 2. Both fields map to the customer ID in the data warehouse. Support System 1 uses ticket ID, which is equivalent to Support System 2's issue ID. Support System 1 uses the subject field, which maps to the description field in Support System 2. Also, Support System 1 uses a priority rating of high, medium, and low, whereas Support System 2 uses numeric values of 1, 2, and 3. In terms of format, the ticket systems export JSON files, and the storage target will be an S3 bucket. Based on the requirement, the engineer needs to filter the source to get tickets with the status of open, solved, or closed, and the date range should be limited to tickets that were created or updated during 2020. In terms of how to organize the data in Amazon S3, the need to access by sales region means that the bucket should be set up with prefixes or folders to match each sales region. Then, AWS Identity and Access Management, IAM policies, can be set up to grant access by sales region. Analysts should be able to query this data and combine it with customer data that is stored in the data warehouse. Based on the exploratory nature of this request and the type of data, the easiest option is to use Microsoft Excel to import and wrangle the support ticket data. Then the updated data set can be exported to CSV. The data engineer uses this information to decide how to extract the data and structure it for ingestion. Here are a few key points to summarize this section. Data discovery is an iterative process that each role who is involved in the business need should perform. During data discovery, the data engineer should determine the relationship between sources, how to filter the sources, and how to organize the data in the target storage. The discovery phase helps you to identify the tools and resources that you'll need to move forward. This section looks at the data structuring step of the data wrangling process. This is the second defined step within the data wrangling process following discovery. Data structuring is about mapping data from the source file or files into a format that supports combining it with other data and storing it for its intended purpose. A key goal of this step is optimizing the structure of the raw data set to minimize costs and maximize the performance of your processing pipeline. Key tasks in data structuring include the following: organize storage, parse the source file or files, map fields, and manage file size. Data structuring involves implementing the decisions that you made during discovery and structuring your source file. First, you need to create any infrastructure that is needed to organize the incoming data and set up appropriate access controls. For example, create IAM access policies for each S3 bucket that you create to segment the files, or set up access control on tables in your data warehouse. By parsing the source file, you can convert defined strings or patterns in the source into formats that can store the strings in structured tables or categorize data in the data lake. Your parsing approach might be straightforward if you're using structured or semi-structured source files. But for unstructured sources, you might need to explore the data to find the relevant patterns, for example, pulling out error codes from within a log file. In addition to parsing the file into relevant fields or attributes, you need to map fields in the source file to the appropriate fields in your target storage. For example, you might map a field called requester ID in the source file to a field called customer ID in your target. Another decision that you need to make as part of data structuring is how you will optimize file size for storage and retrieval. This might mean splitting up large files or combining small files. You'd also probably apply a compression mechanism before saving your files to the data lake. Your data structuring process might be simple. For example, you could import a file into Excel, organize its columns, delete the columns you don't need. You could update column names to match fields in your storage target, export it as a CSV file, compress it, and upload it to a designated S3 bucket and folder. For high volume, high velocity, or complex data ingestion, you would typically use an ingestion tool, scripts, or batch jobs to automatically parse, map, and apply the desired structure to your incoming data and move it to the target location. For the scenario that was described, the structuring step includes exporting a JSON file from the customer support ticket system, loading the JSON file into Excel, and letting Excel parse the file. For the mapping step, for the SUP2 data, the data engineer would modify the cust_num field to match the customer ID field in the data warehouse. The engineer would modify the issue ID, description, and close date columns to match what's in SUP1. For this example, you would perform additional data wrangling steps before compressing the file for upload to the S3 bucket. Here are a few key points to summarize this section. Data structuring is about mapping raw data from the source file or files into a format that supports storing it and combining it with other data. During the structuring step, you need to parse the file, map source fields to target fields, and establish the structures that are necessary in the target to organize the data set. Your structuring decisions should also include the best ways to optimize file size. This section looks at the data cleaning step of the data wrangling process. The cleaning step is the third defined step within the data wrangling process, following structuring. In the data cleaning step, you start to make the raw data ready for use in your pipeline. Usually at this step, cleaning is per source, based on the characteristics of that source. Data cleaning includes tasks such as the following: remove unwanted data, fill in missing data values, validate or modify data types, and fix outliers. Depending on who does the cleaning, the methods and results might be different. For example, a data engineer who is only responsible for successfully loading the data into the pipeline might make sure that blank fields are replaced with values that fit the data type. However, a data analyst might replace blanks by adding corrected values. Let's look at each task in a bit more detail. Even when you intend to load data into your data lake for a variety of use cases, there are elements that you don't want to store. For example, columns that include PII or fields that aren't relevant for analysis. You would also want to remove duplicate values that are present in the source file. You might need to remove values that don't represent the intended contents for a field or attribute. For example, a field with corrupted data or unwanted characters that won't conform to the target's requirements or that would prevent the row from being joined with other related data successfully. Data cleaning also addresses missing data. For example, fields that are blank might need to be converted to zeros if the field should represent a number. You might also need to fill in data for mandatory fields so that the dataset will load into a target structure. For example, if the target table expects a postal code for each record, but your source has some records that are missing this field, the cleaning process would need to put a generic value in to replace the missing value. Another cleaning step that helps to ensure that the data being ingested can be stored and referenced as intended is to validate the data types in the source file match the target and to modify those that don't. For example, if the source file stores dates as a text string and the target requires a specifically formatted date field, you would need to convert the strings to properly formatted date fields. One cleaning step that might require a bit more analysis is to identify outliers and either remove them from the dataset or fix them at the source. A data engineer might run a script that identifies values that are far outside the range of other data values and remove those rows. A data analyst or data scientist might dig deeper to determine if the outlier is an error that should be fixed at the source or data that should be discarded. In the example presented here, the value of 4200 in row 5 was an outlier. The analyst replaced it with 42. Using the example provided, the cleaning step would include replacing the blank customer ID with a placeholder that uses the correct number of digits so that the dataset will load into the data warehouse. Depending on the use case, the data engineer might pass the file to the data analyst to directly correct the customer ID. Another cleaning task that's illustrated is removing corrupted data in column C that was pasted into the subject from an error message. The data engineer recognizes that some of the special characters could create issues when loading the data or trying to analyze it. The final cleaning step for this example is to validate and modify data types. In the example, the data engineer modifies the numeric priority values such as 1, 2, and 3 to match the text values in the other ticket system. The engineer maps 1 to high, 2 to medium, and 3 to low. They also modify the date fields to match the timestamp format that the data warehouse uses. Here are a few key points to summarize this section. Data cleaning is about preparing the raw data for use in a pipeline. Cleaning is usually done per source and includes tasks such as removing duplicates, fixing values, and adjusting data types. This section looks at the data enriching step of the data wrangling process. This is the fourth defined step within the data wrangling process following cleaning. In the data enriching step, you start to pull together related data from disparate sources to create the data set that you need for your analysis. At this stage, you start to merge or combine data from different sources to support your use case. Data enriching could be relatively simple, such as merging similar files from multiple sources. For example, you could combine the support tickets from Ticket System 1 and Ticket System 2. This step could also be much more complex. The Elements of Data module presents an example where public health data is combined with customer data from a healthcare provider's patient system, plus event data from a mobile app that monitors heart rate. This would require a much higher level of transformation and processing to merge these three very different sources into a data set to be analyzed or acted upon. Enriching might also include aggregations or other calculations that are added as new fields to the data set. Using the support ticket example, the primary enriching step is to combine the two sets of support ticket files into a single file. Assuming that you use Excel to perform the same set of structuring and cleaning steps on the export from SUP1, the enriching step would start with appending the SUP1 data to the bottom of the SUP2 data, making sure that all the columns match up. Because the intent in the example scenario is to access the ticket information based on the sales region, the data engineer might query the sales system to get the sales owner by customer ID and use that to create a script to add the sales region column to all rows in the combined file. An optional enriching step might be for the data analyst to review the tickets for the SUP2 system and categorize the subjects into ticket types. This would make it possible to organize the tickets into categories that are similar to the ticket types in SUP1. This might be done by manual review in this example, but on a larger scale, this might be a step that happens later as its own processing step. For example, an ML model might be run against the data that is stored in the data lake to perform analysis on the ticket subjects to determine whether they represent problems or questions. Here are a couple of key points to summarize this section. The data enriching step is about pulling together related data from disparate sources to create the data set that you need for your analysis. During enriching, you might merge sources, add additional fields, or calculate new values.